So here's the fundamental theorem of calculus version 2. I'm going to start out with a function little f, and I'm going to assume that it's continuous. And then I'm going to define a new function which is defined as a definite integral. G of x is the integral from a to x of f of t dt. Now, I want to emphasize here, because it's the first time that I'm writing something like this, that this is a fairly complicated gadget. It plays a very basic and very fundamental but simple role, but it nevertheless is a little complicated. What's happening here is that the upper limit I've now called x, and the variable t is ranging between a and x, and that a and the x are fixed when I calculate the integral. And the t is what's called the dummy variable. It's the variable of integration. You'll see a lot of people who will mix this x with this t. And if you do that, you will get confused, potentially hopelessly confused in this class. In 1802, you will be completely lost if you do that. So don't do it. Don't mix these two guys up. All right? It's actually done by many people in textbooks, and it's fairly careless, especially in old-fashioned textbooks. But don't do it. All right, so here we have this g of x. Now remember, this g of x really does make sense. If you give me an a and you give me an x, I can figure out what this is because I can figure out the Riemann sums. Of course, I need to know what the function is too. But anyway, we have a numerical procedure for figuring out what the function g is. Now, as is suggested by this mysterious letter x being in the place where it is, I'm actually going to vary x. So the conclusion is that if this is true, and this is just a parenthesis, not part of the theorem, it's just an indication of what the notation means, then g prime equals f. Let me first explain what the significance of this theorem is from the point of view of differential equations. G of x solves the differential equation y prime equals f of x. So y prime equals f. I shouldn't you put the x in if I got it here. With the condition y of a is equal to 0. So it solves this pair of conditions here. The rate of change and the initial position is specified here because when you integrate from a to a, you get 0 always. And what this theorem says is you can always solve that equation. When we did differential equations, I said that already. I said we'll treat these as always solved. Well, here's the reason. We have a numerical procedure for computing things like this. We can always solve this equation.